Okay, so within geotechnical engineering, problems can be divided into two types. You get one problem, which are called elasticity problems, and you get problems in the form of plasticity. So, plasticity problems. Now, what do we mean by elasticity problems? So that's stuff like, deformation, which we're used to. We're used to calculating deformation and settlement. But then you have plasticity problems. Now this is looking more at stability, right? So another way you can think of it, if we were to put it in terms of design philosophy, this is serviceability. And this is ultimate. Right? So the codes refer to the stability problem as ultimate limit state. The only thing is that the codes don't specify how ultimate limit state is required. So there are multiple ways in which you could calculate ultimate limit state for your soil, for your structure. And so this video will obviously be focusing on plasticity problems. So one sort of method is called the direct method. Right, so seeing as the codes don't specify a way in which you can solve stability problems for geotechnical structures, you don't have to, the code doesn't sort of tell you have to do it this way. So we can use the approach of a direct method. And this is, plasticity method. So the direct method, there are three ways. So far we have, in geotechnical engineering, you have, it can be divided into two. You have elasticity problems and plasticity problems. Basically serviceability and ultimate. Serviceability is looking at deformations and settlement. Ultimate is looking at stability. Okay, so one way of calculating your stability of your soil and system is through the direct method. Within direct method you have three branches. So the first one is called limit analysis, right? Within limit analysis you have the upper bound and you have the lower bound. Okay, then you have limit equilibrium, and then you have something called the slip line method, or we'll call it let's call it slip line method. Okay, so the whole idea is that we will be looking at limit equilibrium and limit analysis, and we'll look at different ways engineers such as Coulomb and Rankine approached limit equilibrium, and how we go about doing the upper bound and the lower bound. So that's sort of an introduction as to where limit analysis and limit equilibrium fall under in all of geotechnical engineering. In terms of which one is most commonly used, that would be this one, limit equilibrium. That's most commonly used in geotechnical engineering. So if you are going for plasticity problems, you're usually using the limit equilibrium. So that's the first one. That's the first problems we'll look at. But let's go over some specific theory. So obviously this diagram that we made stands for all different types of structures. You know, it could stand for a retaining wall, soil behind a retaining wall, soil under a foundation, you know, all that kind of stuff. We don't look at soil on its own, we look at soil so that we can build stuff on it. So yeah, so I'm going to go over some theory with regards to retaining walls, which is specifically looking at earth pressures. So let me just get the diagram up. Alright, so we've got the diagram up. So this is the different ways in which soil can behave behind a retaining wall. The first one is called the at rest, so that's this one. It's that. Yep, the diagram's a bit weird. That wall movement is part of the next one. But at rest basically means no wall movement. So this basically means if you had, for example, some soil, and you put sort of a wall there to excavate this. So you ended up with basically this scenario going on, right? There's no soil here, and what you have, so I'll just draw that straight so it doesn't look like the wall's moving. So now you'd have this scenario because you've excavated, right? So here is soil. At rest condition means that you don't want the wall to move. You basically want this soil here to think as if there is soil here. That's why, and that's why it should stay at rest. It shouldn't move. There shouldn't be any sort of movement. So that's the at rest condition, and that's defined by K0 here. I'm going to line that K0. Right. So Rankine, which you're probably familiar with, set up some coefficients and denoted that when you're at the at rest position, your K0, your K value is K0, and we'll go on to that once we get into examples. But mainly the whole point of talking about this is what does at rest, what does passive, what does active mean? Right. So let's move on to active. So active. Let me rub this out. So active is the next. Passive is the next one, and it basically means that if this system were to fail, it would fail by the wall moving towards soil, and the soil failing in that direction as shown. Now you might think to yourself, why does the soil fail that way? It can fail that way. It just needs a lot of force to make it fail that way, and that will be evident in the calculations that we make. So you'll see that for the passive, for the force required in the wall to retain that soil in the passive case is going to be much higher than the active case, because it's harder to press soil than it is for soil to push on something else. Right? So the passive case is when the wall pushes onto the soil to the point where the soil moves up the slope and fails. Your active case is the complete opposite. It's when there's too much soil behind the wall that the wall can hold all that soil. It cannot retain all that soil behind it, so the wall moves to the left as shown. Right? So that's the whole idea of at rest, passive and active. It's pretty straightforward. You guys will be familiar that Ka refers to the earth pressure coefficient for active state, and Kp is your earth pressure coefficient for your passive. And you'll notice that obviously mathematically Kp is the largest for the reasons that I just mentioned, that you require a lot of force to end up moving the wall in that direction because the soil is so heavy. Okay, so that's a bit of theory. Let's jump straight into a question. So first thing we're looking at is limit. Let me zoom in. Is limit equilibrium. We mentioned earlier that there are two ways of, or two modes of carrying out limit equilibrium, and it's through either Coulomb's method or Rankine's method. So we'll cover both for the same example and compare values and see what happens. Right, so this is according to Atkinson. He says that the limit equilibrium method is by far the most commonly used analysis for the stability of geotechnical structures, which is what we said in the first slide. And he said that the limit equilibrium method combines features of the upper and lower bound methods. So don't confuse limit equilibrium to it being part of limit analysis, which looks at upper bound and lower bound. Limit equilibrium is a completely separate, direct method for calculating your true collapse load for purposes. It's just different methods. You know, we mentioned there are three. There's the limit analysis, limit equilibrium, and stress field, or the slipline method. Right? So that's sort of an idea of limit equilibrium. Now, one thing to remember about limit equilibrium is that, you know, there's the term limit here. Limit means start to collapse. So we're looking at it just, we want to know what load does a structure collapse. Okay, so I'm gonna quickly draw the scenario. We're gonna use Coulomb's method first in solving the problem that I'm about to show you. Okay, so the question asks, figure 3 shows a retaining wall with active earth pressure. So from the ones that we discussed, we're looking at the active case. It's an active pressure problem. The question asks, what horizontal load is required to cause the soil to fail based on the failure mechanism shown? Assume the self-weight, it says assume self-weight, so the soil will have weight. Gamma dry is 20 kilonewton per meter squared, as we've got. This is 2D analysis, that's why it's kilonewton per meter squared. So you can think of this as, because usually gamma is kilonewton per meter cube, but you can think of it as kilonewton per meter squared per meter width into the page. So that's why we have gamma is per meter squared. And your phi, your friction angle, is 30 degrees. Find the force PA using a limit equilibrium approach. Assume no shear at wall soil surfaces, so i.e. the wall is smooth and the wall is weightless. Right? So I just want to add to this diagram that we could say that we want to calculate W, which is basically the weight of the soil. And the weight of soil is just this triangle here. Okay, so let's begin. Now the way Coulomb works is that he resolves his angles in order to get n in an equation and s. The ultimate goal is that we want to find out what this is, right? So I'm going to circle it in red to remind us. So I'll even write it down. Find PA. That's all it wants. Find PA where this structure will fail. Okay. So the first step is to resolve. Now, given this diagram, we could resolve horizontally and vertically, but I find it easier to resolve parallel to the slope and perpendicular to the slope. That's because your numbers turn out better. So let's do that. Let's resolve perpendicular first. So resolving perpendicular to slope. Okay. Zoom out so you can see both this wall, and in terms of trigonometry, this should also be 45 based on z angles. I'll write that better. Okay, so let's resolve perpendicular to the slope. Okay, so what's going perpendicular to the slope? Well, we only have n. We have n traveling in this direction, and we have no other force that can be resolved into that direction. Everything else is either perpendicular, so s won't be included in this for obvious reasons. It's perpendicular to the axes that we're looking at. We're basically interested in this axis. This is the axis perpendicular to the slope, right? So we need to resolve this angle W, and we need to resolve PA. So in terms of trigonometry, if we were to sort of create a local axis for W, the same way that this would be 45 degrees, this 45 degrees, and conveniently, because this is 90 degrees, this should also be 45 degrees. So for this question, it's quite easy if you've been given 45 degrees, because you basically know that the angles are all going to be 45. So let's draw local axes for this one as well. This one will be 45 degrees based on this here. And because these axes are intersecting at right angles, this should also be 45 degrees. I mean, it's basic trig. I've only provided this just in case you find it difficult to resolve your angles. But yeah, we were resolving perpendicular to the slope. So, okay, so we got that. So now we can do W cos 45. You can even do you can even do sine 45. Just to remind you, cos 45 equals sine 45, and you can plug that into your calculator to reassure yourself. Plus PA sine 45. And now we can resolve, so that's what we've done so far. Remember, we're using the Coulomb. You might be thinking, where does the Ka, the Kp and all that stuff? All that stuff's under Rankine. Coulomb doesn't use that in his equations. So let's resolve parallel to slope. So parallel, we're basically looking at, so S is traveling up that axis, so we'll say S. Is anything traveling down? Anything else traveling up? Yes. We also have P, so I can do plus PA cos 45. PA cos 45. Anything else traveling up it? No. So W is traveling down it at W cos 45. And we can rearrange to make S the subject. I'll explain why in a second, as to why we're making S the subject. Minus PA cos 45. Right? So we have these two equations. So let me just copy and paste them to the next slide. Alright, so I'll borrow it over to the next page. Okay, now so this is something you might remember if you did mechanics at A level. At limiting friction, which in this case is S, S equals N tan phi. That's basically more Coulomb's failure criteria. It's usually in the form of tau N tan phi plus C. Now we're dealing with, we haven't been given cohesion. So we've assumed for this question it's cohesionless. It doesn't cause any problem if it were cohesive or not. But for this one, we'll just make it simpler. We're just going to say that it's a cohesionless soil, which is basically sand. And so yeah, so we end up with this. So this is, this is the same thing as this. It's the more Coulomb failure criteria. And just to remind you, S is that friction force there between the soil that's failing and the soil that's at rest. That's also called a slip line, because that's literally where the soil is slipping. In terms of knowing the direction of that, I don't touch on that. The direction of that isn't too important, because your answer will just end up being negative. But in terms of, if you think about in an active case, we said that, so if I go back to this diagram, in the inactive case, we said that this soil will, fail in that direction, as shown by the arrow. Do it in a different color. In that direction. So friction is obviously going to be in the up direction, right? In order to create that friction force. If they're both traveling in the same direction, then you won't have any friction. So that's where we've got the direction of S. So just to remind you, S is that, it's your friction force, also your shear force. Because I shouldn't have to say this, but soils fail by friction. They fail through shear. Shear is their strength parameter. If you exceed their strength parameter, it fails. Alright, so we've got that relationship. Let's try speed this up. You may have saw this, you may have remember this from A levels as FR equals mu R, if you want to think of it that way as well. Okay. Right. So so let's sub in this equation for this n, and sub this in for S. So we end up with W cos 45 minus PA cos 45 equals, open bracket, W cos 45 plus PA sine 45 multiply by tan phi. So in terms of substitutions, we did this goes into this, and this goes into this, and we end up with that equation at the end. Okay, so now it's just a matter of making PA the subject, and that's quite straightforward. So I'm gonna zoom in, right, smaller. W cos 45 minus PA cos 45 equals W cos, I'm going to expand the brackets on the right hand side, cos 45 tan, we know that phi is 30, so I'm going to plug it in, plus PA sine 45 tan 30. If we take it to the other side, we're going to make the PA's, all the PA terms on one side and all the W on the one side. W cos 45 minus W cos 45 tan 30 equals PA cos 45 plus PA sine 45 tan 30. I'm going to factorize cos 45 minus cos 45 tan 30 equals PA cos 45 plus sine 45 tan 30. So PA equals W cos 45 minus cos 45 tan 30 over cos 45 plus sine 45 tan 30. Alright, I'm going to make this look slightly better. If we know that cos 45 equals sine 45 and cos 45 and sine 45 in every term, I can just cancel them out. So that, because they're all equal to root 2 over 2 or something like that. 2 over root 2, one of those. So I end up with W 1 minus tan 30 1 plus tan 30. Alright, now what's W? W is so we've got gamma tri, which is this, and it's in meters squared. So you can just think, if you want a force, just multiply by an area. So I'm going to do 20 multiplied by this triangle, the area of this triangle. That will give me my W. Now you might want to know how to derive that. So I'm going to copy this triangle over. Alright, so I've copied it over. So we're going to we need to work out the area of that triangle. So area of triangle equals, we've got the height, which is 4. We need to multiply by the base. So we could use, let me just rub out some stuff. We could use this length here. And the way you do that is you can use the relationship of tan. So tan 45. You're basically your software rules. So tan of this angle 45 equals the opposite. We'll call this let's say x over, well, let's say opposite over adjacent, as we all usually do. Opposite over adjacent. So O is basically A tan 45. A in this case is 4. So it's going to be 4 tan 45 divided by 2 to give you the area of the triangle, because that was the area of a rectangle. So just as a reminder, if this is O, this is A, which equals 4, and that's 45, get that relationship. Okay. So your force, so W equals 4 times 4. Tan 45 is 1, so I'm just going to do it as 4 times 4 over 2. So 8. W is 8. 8 kilonewtons. Okay. You can always develop a generic formula for W. So W is 8 kilonewtons. So P is therefore 8, 1 minus tan 30, 1 plus tan 30, which equals, sorry, I made a quick mistake, I forgot to multiply it by 20, so it's multiplied by 20, so that's 160. Yeah, that cancels out with that. You end up with, yeah, take it to the other side. So yeah, that for some reason seemed really small. 160 kilonewtons. If I now sub in, we end up with 42.87 kilonewtons, which is correct. That's the answer. That's the P force that you need, the active force that you need, in order to make that geotechnical structure fail. Okay, so that was for the passive case. The next question asks you to use the same method, this Coulomb's method, for limit equilibrium, to work out in the case of a passive. So it will be called PP. Now I won't cover it, but what I would say is that the only thing that changes is that the P is still facing that way. You just change it to PP. The only thing that does change is the direction of S. The direction of S is now going downwards. Now you could think of that as, that's the only change. That will give you your passive force. And if you think of that, why that is the case, if I go back to these drawings, there we said that because the soil fails in the downward motion, down the slope, your resistance would be up the slope. Same thing is the case here. Now your soil is going up the slope, so your resistance would be down the slope. So can you see the alternation in? So this is happening here, this is happening here. So you always want to resist your motion. That's your friction force. But other than that, there wouldn't be any difference. You would resolve the same way, calculate the same way. Your P ends up being, your value for it ends up being 597.13 kilonewtons, which, as we said, is about 10 times bigger. It's more than 10 times bigger than our active force. That's because if you think about it logically, it's harder to push a force, push soil up a slope than for the soil to move down the slope. But yeah, that's that.